So let's get going. So last class, we introduced two important definitions. We defined what's called random variables and a probability distribution. So again, one of my advices for students learning things for the first time is do not get overwhelmed with those definitions we wrote down, but rather think in terms of examples. And one of the reasons I've beaten over the head the three common examples over and over again is that hopefully you guys will see the use in that. We've talked a ton about flipping coins. We've talked a ton about rolling dice. And we've talked a ton about cards. And so what we'd like to do is we would like to use those examples and so we can think of them in a certain way. So let's illustrate an example. So to illustrate, consider flipping a coin 3 times. So this is similar to what we did on Monday. Monday, I think we said, let's flip it 4 times. Let X be the number of heads. Then X is a random variable. So remember, a random variable is a function whose inputs are elements of the sample space, and then its output is a numeric value. So then f of, say, k, which is equal to the probability that x equals some value k, is called a distribution function. So we showed you a couple ways to visualize this last class. Let's do a simple one now. We can visualize f as follows. So the analogy here is similar to what you were when you first learned in an algebra class, maybe in high school or middle school, where you talked about inputs and outputs of functions. You can make a little table. So you can have the random variable up top, and then you can have the probability of the random variable equaling certain values. And so what are the options for the random variable? How many heads can I get? I can get 0, I can get 1, I can have 2, or I can have 3 heads. And if I have three heads, excuse me, you could write all this out if you'd like, but perhaps a better way of doing this is to use the shortcuts we talked about last week. And that is, how do I get 0 heads? Well, that means that I get all tails. So that's 1/2 times 1/2 times 1/2. And so there's 8, one of the 8 ways gives you that. How do I get 1 head? Well, I can get a head in 3 different positions, first, second, or third. So that is 3/8. And then how do I get 2 heads? Well, that's also 3/8 and then 1/8. So this is, in fact, a probability distribution. Okay, does anybody have a question or comment? So again, all the possible situations are on the horizontal part of this table, and then their corresponding probabilities are below. So here is a question of, on one hand, theoretical importance, but also curiosity. So here's something that we might ask. Question. Suppose we repeated this experiment many times. On average, what do we expect as the number of heads? So, I mean, let me make this a little more clear, because I don't know if it is clear. Suppose we did, suppose I said to you, okay, every one of you goes home and there's, say, 30 students in this class, and I said, you do the experiment 10 times. So each one of you does the experiment 10 times, and then 10 times 30 is 300. And then we can put all our data. You could say, okay, these times I got this many heads, that time I got this many heads, etc. And then we can ask, on average, how many heads did we get in all 300 trials? Let me repeat this again, because I think it's important if you want to learn this at least. If we did this experiment, say 300 times, what would be the average number of heads? So you did the experiment, you take the first try, you count the number of heads, the second, third, fourth, you add them all up and divide by 300. Now we could go to a computer and we could run that for sure. And that's great, but there's got to be some sort of theoretical way we can study this based on our axioms. And it turns out that there is. And the way that we do it is we make some definitions. So there is a theoretical way to answer this, or there's a theoretical way to study this idea. And it's called the expected value, or I guess we should call it the mean for now. We shouldn't get ahead of ourselves. So let's guess we'll call So there's two sort of synonyms for this. You could call it the expected value of a random variable, or also known as the mean of the probability distribution. And luckily, it's very similar to things we have done already. Okay, so what is this expected value? What does this mean business? So how is it defined? It's defined by the Greek letter mu, or we write capital E of X for expectation. And so we write mu is equal to, now this is going to look scary, so we have to write down some general things. So what we typically do is we use shorthand. And one of the shorthands that we use in mathematics and statistics and science in general is we use subscripts. So suppose we have an experiment that has n outcomes. So we would like to know, then we have this random variable, it can take on n of these outcomes. So one way we can illustrate that is we can say, okay, we have the first outcome, and the mean is going to be defined by multiplying that by the probability that that first outcome happens. And then we take the second outcome times the probability that that occurs. And we do this for all the outcomes. Now, this looks very overwhelming right now. I understand that, but we're going to do it in the specific case, the example we just did before, and hopefully it makes a little more sense when we do that. So what are x sub 1, x sub 2, etc.? These are the outcomes. And these are their corresponding probabilities. So again, do not get overwhelmed with this rate yet. Once, do not try to memorize this formula. Just try to think about the pattern in the formula. And we're going to do an example in a second. Okay, so again, do not get overwhelmed. Let's go right to an example. So in fact, we'll do the example we just did. So let's toss a coin 3 times and count heads. So what are our options? Well, our options are, the first event is X sub 1, where we get 0 heads. X sub 2 would be 1. That would be 1 head. X sub 3 would be 2. That would be 2 heads. And X sub 4 would be the 4th scenario. And the 4th scenario is that we get 3 heads. And then what are their corresponding probabilities? Well, the probability that X sub 1 happens is 1/8. Probability that X sub 2 happens is 3/8. The probability that X sub 3 happens is 3/8. And the probability that the 4th scenario occurs is 1/8. And by the way, I'm not just, these numbers are coming from the, we just did this example right here. This is where I'm getting these numbers from. So it's not like I'm doing some rapid things in my brain. Does anybody have a question about this? Okay, so what does the mean become then? Well, the mean is 0 times 1/8 plus 1 times 3/8 plus 2 times 3/8 plus 3 times 1/8. And of course, this is, the first one is 0, so you're left with 3 plus 6 plus 3. So again, 3, 6, and 3. So that's 12/8. Which we can round, or round, excuse me, write as a decimal. So I guess I shouldn't put approximately. 12/8 is not. 8 goes into 12 one time. The remainder of 4/8. So this is nothing more than 1.5. Now, this should make intuitive sense to you, I would think. If you're flipping a coin 3 times, and the coin is fair, well, then you'd figure if you did it a couple times, you'd get 1 head these times, 2 heads the next time, because those are the most likely outcomes. And then you would think on average that 1.5 shouldn't surprise you. Does anybody have a question or a comment about this? Now, how do you interpret this? I mean, clearly you can't get 1.5 heads in an experiment. And that's why we say this is a theoretical value. What this is suggesting is that if you did this experiment, say a couple thousand times, and you took the average result of the heads each time, your number would be 1.5. Does anybody have a comment or a question? So what we could do, and we're not going to do it right now, maybe I'll show it. I guess I can do it later for this and other examples, is we could simulate. I can go to the computer and simulate the coin toss. And if we averaged it out, you would see, much like we've seen in the past with these other examples, that we were left with 1.5. All right. So this is what we call the mean or the expected value for a random variable probability distribution. Okay, so then another sort of way we can quantify what's happening is we can talk about the variance or standard deviation for a probability distribution. And this is a little more complicated of a formula, and you might recall that, yeah, it was complicated when we did variance for just a group of data. So this is quite scary, but we're going to have to go with it anyhow. So the variance of a distribution, a probability, is, and this is scary. So remember, we'll do sigma squared. And so we take x sub 1 minus the mean squared times the probability of x sub 1 plus x sub 2 minus mu squared times the probability of x sub 2. And this crazy pattern happens for all n of the outcomes. So as you can see, this is not always easy to compute. And then, of course, the standard deviation is sigma. So you take the square root. So maybe we'll write it here. Yikes. So again, this is not always, easy to work with. Does anybody have a comment or question? So one of the things we'll ask you to do for homework is do the probability of the variance for the problem we just did, where x of 1, or excuse me, where x is the random variable, the number of heads. It's not a difficult problem to do. It's just it's a little tedious. Okay. Does anybody have a question? Yes. Oh, no, that's not a question. That's someone joining the party. Okay, so let's look at an example that again has some applications that we've sort of alluded to in some of these problems, particularly those bonus questions I asked on the last homework. So we'll start very basic. So the mean in same thing as expected value can be used to determine what I like to call fairness and so then you can judge on things like, should I play this gambling game, or should I buy money for this lottery? So let's look at an example. So a lottery is held, and let's say 10,000 tickets are sold. And let's say each ticket is sold for $2 a piece. And let's say there is one winner. Of the lottery, and it pays, let's say, $1 million. $1 million. So the question that you might ask yourself is, should you buy a ticket? So some people would maybe reason, well, let's spend $2 for the chance of winning $1 million. So let's think about how we might analyze this. But in order to analyze it using the tools we have, we need to formulate this problem properly. What we'd like to do is we'd like to think about, we need a random variable, we need a probability distribution. And then once we have that, we can use the mean or the expected value, because what that's going to tell us is what do we expect to happen. So let's think about how we might set this up. Here's one setup. I'm not saying it's the only way to do it. So let X be the random variable. Of your financial gain. If you buy one ticket. So what does that mean? X can mean one of two things. What is your financial gain? Well, if you win and you lose, there are two different things. So X has two options. The first option is if you lose, let's say, then you are out $2 because you bought ticket price. So I am going to use a minus sign to illustrate that you didn't gain $2, you lost $2. Now, if I happen to win, what I've done is I've gained $999,998. So why is that what I gained? Well, because I have my winnings minus the $2 I used to buy the ticket. Does anybody have a question about this? I'm not saying you have to do it this way. I'm saying this is one way to set it up. Because each one of these has a corresponding probability. So we can even, to make this clear, we can call this the first one and this the second one. And then the probability that X1 occurs, what's the probability you lose? Well, that's very high. That's 999,999 because there's only one winning ticket, and that's out of 1 million. And then the probability that you happen to win is 1 over 100, or excuse me, 1 million. And so our expected gain here is mu, and that equals, well, what do we have? We have -2 times this. Plus our winnings have, if we happen to win, times the probability that we won. And so we will not drive ourselves too crazy trying to do this by hand. I'll go right to a calculator. As you should too. So if I do this,
Yeah, she's right. You said 10,000 tickets instead of 1,000,000 tickets.
oh, I did.
Yeah, your
Well,
chance
what are
to
you guys
win.
waiting for to tell me this then? Why are we waiting so long? Well, here's an idea. Here's what we can do to fix said error. Here's how we fix L error. Let's go back. Did I say 10,000? No. Now, in order to, we said it pays 1,000,000, right? Isn't that what we said? So it pays 1,000,000. That's the winnings. Very good catch. And so that's your winnings. But the number of tickets would be, this is what needs fixed, correct? So let's fix this. And then of course, these would be need fixed. So the probability that you lose is, if you're out of 10,000, correct? Then that would be what? The probability that you lose, and that the probability that you win is 1 out of 10,000. So what's left here? It's 9,999, correct? We in agreement now? Does that fix the problem? I believe so. So this is the millions. Okay, very good. So these numbers need to add up. Very good, very good, very good. Okay, now we can plug this in. So the probability that we lose times what happens to our financial wherewithal if we lose is this. And then over here we have this. So now we go to our calculators, assuming we didn't make any more errors, which we now know is possible to do. Now, the only question is, did I do that on purpose? Or one never knows. So do not forget to subtract. So if you plug this into a calculator and you do it correctly, what you end up getting is an exact number of 98. So what are we suggesting here? What are we suggesting, or what does this suggest?
Don't buy the ticket because you're not going to win.
Well, that's not necessarily what it means. It actually, it actually means that maybe it's not such a bad bet after all. Because in the long run, you're not losing money. Now, if the number I got, we're going to do another example in a second so you can see the contrast of what we mean by this. But one way to interpret this is, instead of saying don't buy the ticket, one way to interpret this is, if you were to play, say this lottery happened every day. Say all they sold was 10,000 tickets and you had a chance to win $1 million. What this is saying is that if you played every day, theoretically, you would eventually win, right? And those winnings would override all the times you've lost. But the problem is this says nothing about how many times we would have to play before we likely won. So I wouldn't go ahead and say that it says not to play, because it's not really saying that, although it depends on how you interpret it, I expect, or I suspect. Because the thing is this jackpot is so large, $1 million, that winning once would cancel out all the losses you had. Does that make any sense? Now, what you would imagine is if we sold more than 10,000 tickets, then this number would go down. So let's compare this with another example, just so you can sort of see what I mean by that. So for comparison, assume the prize was only, say, $1,000, not $1 million. Then what is your mean? Now your mean is, okay, so what are the two options? You lose $1, or you can lose $2, right? -2 times, what's the probability you lose? Well, if there's 10,000 tickets sold, the probability you lose is the same. 9 over 10,000. Plus, what would your winnings be now? They would only be $990. Excuse me. Fix that. You would subtract 2 from your winnings, so it'd be $998. And what's the probability that you win? It would be 1 over 10,000. So now what happens is when you compute this number, you get -1. So here, in this scenario, or in this lottery, your expected winnings, or your expected gain, is negative. And that maybe shocks or maybe doesn't shock you, but I would ask you to think of it this way. If you played the lottery every day for $2, imagine if you played for a year without winning. Well, if you played for a year without winning, let's just say you played every day of the years. So that's 2 times 360. You've almost lost $1,000 at that point. So even if you happen to win after a year, your net earnings are still very low because you've wasted all that money playing up until the time you won. So hopefully that puts a little perspective on this. So one of the things that casinos do, and this is what makes this stuff very interesting, at least in my opinion, is casinos have a very good way. Well, it's not just casinos, because these gambling games have been around for an extraordinary amount of time. But what makes casinos work, in the lottery in general, is that your expected gain is negative. But it's usually a very small amount of negative expected gain. So what happens is people who go to casinos, they see that someone wins a jackpot all the time. And so those who gamble a lot, even though they might win a jackpot from here to there, typically in the big scheme of things, they are still have lost money to the casino. If I continually go to a slot machine and I put $1 in and pull it, put $1 in and pull it, and I do that for say $60, $70, and then I finally hit for 30, I'm still losing. And very few people who hit a slot machine jackpot for say 5 grand or 10 grand or 30 grand or 100 grand, very few people who have done that have only played a slot machine for 5 or 6 pulls in their life. Typically people who gamble. So in the long run, even if the casino has a jackpot here or there for someone who very rarely, if ever, plays, maybe their only time ever gambling was 3 days in Vegas, there's still enough other people who continually put their money in that the casino's expected gain is always very large and positive. So anyhow, I think it's worthwhile, if you're interested in any of this, to sort of look at these examples and see and compare them and think about, is it worth your while to bet $2 every day in hopes of winning $1 million? Is it worth your while to bet $2 every day in hopes of winning 1,000?
How would we figure out one for blackjack?
Say that again?
So how would we figure out one out for blackjack?
Well, that's a little more complicated. I was just about to tell you. I mean, you also have a little more. Remember, this is a very simple lottery. We're talking about just selling raffle tickets here, right? In context, you're just buying, they're selling 10,000 tickets and one's a winner. Whereas even think about the lottery that you play in the Pennsylvania lottery. You pick numbers. So it's a little more complicated to do this, but in fact, the odds are not in your favor. And by the way, it's worth knowing that if, you know, blackjack is one game where you have, I don't want to say control, but if you know what you're doing, you can increase your sort of expected chances of winning. But it's much more complicated to determine expected values of that hand because there's a lot more happening. You know. By the way, there was this group of nerds years ago in, I believe it was the Massachusetts lottery, and they were students, I believe, at MIT. You'd have to maybe Google search this, but they realized that if they get enough of their friends together and they can put money in, they figured out that there's a magic number that if they buy so many tickets, they are very likely to win these jackpots. And so what they had is they had a scheme where they used math to figure out how many tickets they needed to buy of a certain game so that they were likely to win. And then they did this for a few years and no one cared because they weren't cheating the system. They were, you know, there has to be a winner. It just turns out that they were the winners. So it's kind of like what happens is like people who work together will all go in, they'll all pitch in like $50 and they'll all buy Powerball tickets. But really, when you have a huge lottery with so many entries, you have to buy a sufficient amount before your expected winnings are actually positive. So there's lots of ways you can think about this and analyze this. I think that, in my opinion, I think these are things that are fun to do. And like I joked on Monday, the more of this you understand, the more you can create silly games and take money off your friends. Who doesn't want to do that? All right. Any questions about this? So this is, again, this is a way that we can sort of quantify if a game is fair or not. This game tells you that on average you're going to lose. And if you play this game, it says on average that you might win. But really, if you had a chance of winning $1 million and all you got was $98 out of that, you wouldn't feel like you really won, would you? So that's sort of the way to think about that. Okay, moving along. Before we do that, does anybody have any questions, comments? Well, we could have used other contextual examples too. Another fundamental example that uses these ideas, for example, in financial advising, you might have stocks and bonds that are high risk, but they have high payoffs, and you have to determine should you or should you not invest in certain stocks or certain bonds. Okay, we'll probably assign you some problems like that, and then you ask. So again, the last thing I'll say about this before we move on is the reason I use the word fairness in quotation is because if expected value is 0, that means the game's fair. In the long run, you're the same as where you started. But if your expected value is negative, like it was here, this means it's not in your interest to play. Okay, so anyhow, there's more to talk about, so we have to move on. We need to start sort of making the transition. I know I've sort of been championing this for a while, but we need to make the transition from these coins and these cards and these dice games to more real world things. And so what we'd like to do is, in order to sort of understand how the real world works, we'd like to have a sort of set of tools that we can often use to analyze. And one of the ways that we can do that is we can sort of classify certain types of phenomenon, and we can use different distributions to sort of analyze them. So our next step, now that we know what a probability distribution is we can study specific ones. So now that we know what a distribution is, we can study specific ones. And so the coin toss, as I said, is a specific example of a more general phenomenon, which is win or lose, success, failure, on, off, good, bad. So a coin flip is a special case of a more general thing. For example, win, lose. Pass, fail. I hate to say bad things, but you get the rest. Survive, die. Again, we can go on and on. I guess I'll do one more since I wrote the number 3 down. But here we go. Oh, I can't even say this anymore because what the hell? Oh, you know, someone might get mad at me for this, but I don't know. What else can I use? I was going to say male, female, but someone might say you shouldn't say that, O'Grady.
Corona, not Corona.
There you go. There you go. Positive, negative for the Roni. There you go. You get the idea, right? And I've talked about this before, like, you know, live, die. Alone is default, alone pays. You make money, you lose money. So that's a coin flip is a special case of that. I hope we understand that. So we can put et cetera here. And so that means that any sort of thing that behaves this way might be able to be modeled the way coin flips are modeled. And there's a special type of distribution that helps us for this. So in these situations, we can often model as if it were a coin flip. And what's even cooler is, what's even more useful is we don't even have to assume it's fair. That is, maybe heads is 3 times as likely as tails. So So what situations does this apply? So when does this apply? It applies, first off, suppose we have a fixed number of trials. You know, so what does this mean? This means, okay, I'm going to flip a coin. Six times, 37 times, 15 times, 847 times. So we usually use, say, n trials. Then each trial has 2 outcomes, heads, tails, right? Pass, fail, lives, dies, pays off loan, defaults loan. What we usually do is we call them success and failure. Instead of heads and tails, we'll say success and failure. The other thing that's important that this applies, what do we know about coin flips? The fifth coin flip don't give a darn about the second or third. So what's the fancy way of saying that? If you go back to what we said, we say each trowel is independent. So the fifth thing doesn't care about the second thing. The 14th thing doesn't care about the 10th thing. And then the last thing that we must have to mimic the coin flips is that the following must be true. The probability of S is the same. So the probability of a success is the same for each trowel. And that's exactly how a coin flip was. And rolling 2 dice or 3 dice. The probabilities don't change. Okay, so what do we call these things? By the way, does anybody have a question, comment? I'll just stand around. By the way, no one's in here today. I'm all by myself. What the hell? I should just come in here and dance around. Of course, you guys are all sleeping too. Probably they're daydreaming or playing Call of Duty while listening to me babble. Okay, so all the stuff that we've talked about to this point, believe it or not, is now going to allow us to determine the distribution for this experiment. So anything is satisfying the above 4. So any experiment or real world situation, any experiment satisfying the above is called a binomial experiment. Bi for 2, binomial experiment. Its probabilities are given by, this is going to scare you for a second. They are given by the distribution. I guess I should be more specific. They are given by the binomial distribution. And this is big shorthand for all the stuff we've been doing to this point. So the probability that one of the random variables takes on a number k is given by, you take n choose k, and then you multiply it by the following. You take p to the power k times q. Now this is going to scare the heck out of you, times the power, or to the power n minus k. And what are these things? Where, well, capital P of success, the probability of success is p. The probability of failure is 1 minus p, which we typically denote. Actually, no, let's do it this way. I don't like making a mess of this. Let's keep it more consistent. let's actually, this helps you understand more, I think. So think about this. When we had coins and they were fair, this was 1/2 and this was 1/2. So this is in agreement with our coin formulas we've done. And by the way, another way to write this if you want, if you don't want to use that choose symbol, you can remember what this equals. This is n factorial over n minus k factorial times k factorial, yikes, p to the power k, 1 minus p to the n minus k. Yikes. So, a few of you, and I think if recently as Monday, it was asked, how do we find these probabilities without writing out sample spaces? And now you know, this is it. This is the magical formula that gets it all done. So before we get bombarded with all this scariness, let's just do one example, and then we'll get you out of here, and we'll give you homework, and you'll have heart failure over this. Hopefully not too much. All right, so let's look at an example to see how this works, and we'll go to the one we had before. So assume, let's do 2 examples real quick. So once again, a coin is flipped. Let's go to the one we did before, flipped 3 times. Determine the probability of exactly 1 head. So the way you might think about this is, let's let success equal head. And let's assume it's fair. So the probability of success is the same as the probability of a head, which is 1/2. And then the probability that I get exactly 1 head is 3 choose 1 times 1/2 to a power times 1/2 to the other power. So this is to the power 1, and this is to the power 3 minus 1. And of course, this simplifies. This is 3 factorial over 2 factorial times 1 factorial. And this is 1/2 to the 3rd if you do your exponent properties. And this simplifies to 3 times 1/8, which is 3/8. But we already knew that because we wrote it all out earlier. But it's nice to see this formula gives us the same answer that we had by drawing out the sample space. All right, we're out of time. Does anybody have a question? And we'll have to do more examples of this. But I encourage you to give this some thought. It's quite, I don't know, I think it's quite fascinating, but you might not. Anyhow, if you have questions, let me know. Otherwise, I will see you guys Monday. Do not forget to do the quiz. Please, 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 please. And if you have questions at all, let me know. All right. Thank you guys very much. I will see you next week. Take care.